Innovative IDM has a lot of engineers that can help you with servo sizing, but we decided to bring in some of our great vendor partners today from Yaskawa Motion. And our presenters today are Sixto Morales. He's a motion engineer, regional motion engineer with Yaskawa Motion, and also Michael Petrini, who is an engineer as well. And so, guys, I'm going to turn it over to you. Take it away.
All right. Well, thank you, Pepper, and thank you to everybody who is attending this webinar. We hope that it will be educational and that you'll get a lot out of it. So, as Pepper mentioned, we do have the beginnings of this webinar going on. So it's Michael Petrini, who is the Senior Sales Engineer for the TOLA territory, Texas, Oklahoma, Louisiana, and Arkansas, as well as myself, Sixto Morales. I am the Regional Motion Engineer for the same area, as well as 7 other states, and the International Sales Manager. As Pepper mentioned, in the chat window, we've copied and pasted all these links in here. So if you wanted to get those, you certainly can. So what's the purpose of this webinar? So the purpose of the webinar is just to really provide some tribal knowledge of how to size servo motors for various different applications. And the process that we're going to go through is we will review some common mistakes. These aren't all the mistakes that you're going to get, that you're going to find out there, but just some common mistakes that we see, and review some common servo applications that could be servo motors, some that couldn't. We're going to also review why it's important to sometimes select a gearbox, or what are the criteria for selecting a gearbox. And then we're going to follow it up live with a sizing demonstration and take it from there. So in the end, once it's all done and over with, the payoff for this webinar is that you will get an understanding for why servo sizing and concepts are important, and then be able to make a very good investment comparison. At this point, we wanted to open this up to just show a couple of the typical servo motor applications. So maybe you guys have some of these in your plants, some bottling or labeling applications, maybe some R&D, looking at some gantry systems or some 3D printers. Maybe it's some sort of a tensioning or a winding application where you have to use to maintain tension on a particular process. Let's go outside. Maybe it's some sort of a rack and pinion gantry system whereby it's 20, 30 feet long by 40 feet wide. And then let's start to get a little bit complex with a rotary knife application or a slitter or a sheeter. Let's get really complex, and let's just start pulling some pulleys in various different places to reduce or to make motion for rotating applications. And then maybe some large ones that we can use for some linear actuators, or some linear actuators to make some forward or inverse kinematics. So you guys all have your keyboards out, and in the chat window, if you wouldn't mind, let's take a couple seconds and just type in, what are some of the various applications that we didn't touch on? We'll kind of just take a little pause here and see if there's some applications that you guys can put in there. So please feel free to do that. Okay. Mr. David Cole says, yeah, we got some bag loading, palletizing. Very good. Those are good applications. Okay, yep. Got some other winding. Yep. Okay, good. Well, if you guys continue on typing in the chat window, we can review those at a later point in the presentation. At this point, though, I am going to pass off the floor to my co-host, Mr. Michael Petrini. So, before I do that, sorry. Before I do that, a presentation wouldn't be complete without some sort of marketing. So I promise it's just one slide here. But Yaskawa is a manufacturer of motion control, servo products, variable frequency drives, and robots. We have a lot of servo axes out in the field. Got a lot of VFDs and robots as well. We got over 14,000 associates in 25 different countries, and we are a $4 billion company with many, many more robots and servo axes that are going to be sold. So that was my one marketing slide. Okay, at this point, we're going to pass the floor off to Mr. Michael Petrini.
Thank you, Sixto. Good morning, everyone. Thank you again for joining us for this webinar. We hope you find all this information useful. As a sales engineer with Yaskawa, I get lots of questions about sizing servos, and 9 times out of 10, A lot of people seem to have the same confusion, or at least have the same frustrations when they're sizing servos. So we wanted to take a moment to just talk to you a little bit about some of the common mistakes that people make when they're looking at servos and how you can get ahead of them. So mistake number one is comparing a servo motor to an AC induction motor. The reason why we talk about this is because most people, when they call us, if they have an application for a servo motor, the very first thing that they're going to do is they're going to look at the kilowatt rating on a servo motor and associate that to horsepower on a standard AC motor. It's important that you not do this, and there's a couple of reasons why. So first of all, as we've mentioned, AC motors are rated by horsepower. They typically use a soft starter or a variable frequency drive to start that motor. They are current driven. Typically speaking, asynchronous motors don't have positioning feedback or torque control, with a few exceptions here or there, and they usually have a lower overall initial investment. A servo motor, on the other hand, is identified by kilowatt, not by horsepower. So it's, again, what people normally do here is they're going to say, oh, I have a 1 horsepower motor, I need a 1 kilowatt servo motor. That's usually not enough information just to go forward. The next thing that people forget about with a servo motor is that they usually require a servo amplifier as well. Servo motors have internal feedback. They are very precise in their movements, and they typically have a larger upfront investment. So again, is it okay to use as an induction motor as a guide for sizing a servo motor? No, it's not. Don't fall into this trap. So that's mistake number two, or mistake number one. Mistake number two is ignoring the inertia ratio. This is something very specific to servo motors that you usually don't have to worry about with AC motors, so it's worth elaborating here for just a little bit. So let's say someone calls you up and they say, okay, Michael, I heard what you said about the horsepower. I didn't size my servo based on horsepower. I did it the right way. I sized it based on speed and based on torque. That's all you need, right? No, it's not all we need. There's a little more information that would be really helpful here, and it'll save you a whole lot of stress as you're implementing your motion system. So what are we talking about when we actually talk about the ratio of inertia in a system? Well, what is inertia? Well, again, your high school physics class is probably coming back to haunt you a little bit right now. But basically, inertia is just basically the resistance of anything to move. It's also the resistance of anything to stop moving until it's acted upon by an outside force. So take, for example, throwing a tennis ball. If I were to just grab a tennis ball and toss it to someone, odds are they're going to be able to catch that tennis ball and control it really easily. Now, what happens if that tennis ball turns into a bowling ball and I have to lob it over to you, and then you have to catch it and control it without dropping it? That's where inertia comes into play. And that's why it's really important that we don't factor in just speed or torque, but we also look at the overall inertia. It's also worth mentioning that not only do you have to concern yourself with the load inertia, you also have to concern yourself with the motor inertia as well. Let's take, for example, our tennis ball, or let's go back to our tennis ball example again for just a moment. If I throw a tennis ball, odds are it's going to take me just a little bit of effort to do so, but it's probably going to take even less effort for someone who's like a NFL linebacker or a professional bodybuilder. In that case, just like a servo motor, it takes significantly more power just to get that motor going than it does to actually do the task at hand. So not only is it important to look at the load, but it's also important to look at the motor. Which brings me to my next point. When you're comparing these two, it's important to look at that ratio together as a complete system. So in this case, an easy way to tell if we're sizing a correct motor based off of inertia is to look at the inertia of the load divided by the inertia of the motor. Now, typically speaking, most manufacturers of servo motors can maintain a 10-to-1 ratio, meaning that load can have 10 times the inertia of the motor and the motor can still control it. With proper tuning, our systems at Yaskawa can go even further. So again, that's why it's important to take into account the ratio of inertia, because typically speaking, you can use a much smaller servo motor to get the same task done as a much larger AC motor. Oh, this is a good one. Who's been guilty of this one? Feel free to answer in the chat window if you have a good story about this. But I can promise you, I get phone calls like this all the time. And I call this the competitor crossover trap. It goes something like this. Someone calls me, they say they've got a machine and it's working, but the servo motor just crashed on it. And unfortunately, for whatever reason, they want to look at that servo motor and they want to just pull it out and replace it with a brand new one. That's great. The problem is when people say, okay, I want to replace this old XYZ competitor servo motor with one from Yaskawa because of the known reliability. We know it's great. We know how it works. Awesome. I'm happy to do that for you. Is that going to be a drop-in replacement? No. Typically, that is not going to be a drop-in replacement. Don't fall into this trap. Don't look at just the torque and the speed of your competitor and try to size a servo motor based off of that. Don't look at just the inertia either. Take it one step further. When you look at a competitor's servo motor, bear in mind, not all servo motors are the same. There's different sizes to each servo motor. There's different form factors. There could be different shaft lengths, different shaft widths. Maybe it has a key, maybe it doesn't. There's a lot to factor in here. Odds are the reason why you're calling in the first place is because that original OEM of that piece of equipment is gone. Maybe they're out of business. Maybe they're not supporting you all that well. But the bottom line is, if you want to make sure that you're doing this right, take that information from that crossover. Is it just a guide? Maybe it's something that you double check when you're all done. But don't rely on it completely to be 100% accurate and correct. And again, most of us, if we're doing this anyway, we're going to take that competitor's crossover information and we're probably going to upsize it just to make sure we're covered. So at that point, now you're looking at a servo motor that may be 20%, maybe 30%, maybe 50% high, larger than you really need it to be. So again, there's lots to keep in mind here, and you're much better off doing a full servo sizing from the ground up than just trying to copy someone else's previous information. So with that in mind, Sixto, can you tell us a little more about some of the common servo applications you see in the field?
Why, certainly, Michael, I sure can. So let's review just a couple that we've done over the years. So the typical one is a ball screw, right? Got a gantry, some sort of a gantry style. Take a look at this picture here. This is moving in a horizontal direction. It's going back and forth of some sort. There's some sort of station whereby the x-axis is moving left and right. Some sort of jobs that have to happen. So those types of applications are going to be, there's going to be some sort of precision that's needed for that movement. So the questions that we start asking ourselves are, well, what is the load? What are we moving? What is the payload? How heavy is that? How heavy is that enclosure? How heavy are those brackets? Again, an overall estimation may be good, but if you have a current working system, maybe there are software tools built into the control that's already on that, so you can pull off and say, well, it's really only using ever 5, maybe 10 newton meters of torque, maybe 2. Because remember, if the motor is rated for 4,000 RPM, but your movements are never hitting anywhere to that number, then there's really no need to use a 4,000 RPM motor. So that's one question. The next question, I mean, obviously, as you see here, you know that it's going to be horizontal, but it could also be vertical. So the orientation is important because gravity can affect the motion profile, can affect the payload, which in turn will affect the servo motor as well. This question, what is the speed? And it's kind of a, hypothetically, what's the speed? Well, we typically want the worst case, but we don't want, it's got to be very slow, or it's got to be very fast because it's relative, right? Relative to someone who's moving very slow may think 1,000 RPM and that's slow, whereas somebody else may think, no, that's actually very fast for the machine. So some typical questions that you would start asking about the applications that you see. Change up a little bit here to a rack and pinion system. So still with a gantry style of a system, but let's take it outdoors maybe. Maybe you see that the how far the axis has to travel. This is a pretty big gantry system here. Maybe it's a 40-foot length of travel that you got to go, maybe 30 feet high and 20 feet wide. It can't be just it's got to go just this much or just a little ways. You typically want to have, what the distance is that you want to make a move profile in and to do the travel. So precision, what's the required precision, or how, what's the typical tolerance that you need to stay within? Some applications, they're perfectly fine with staying in within 1/4 of an inch or 1/2 an inch. And some of them have to get into we got to get into the 2 millimeter or the 1 millimeter window. So it varies between application to application what the precision is required. And if you don't know, if you already have a current machine, typically you can guesstimate where you need to be on the precision question. As this application is showing, the environment is going to be outside. So this is in Texas. It's going to see 120, 130 degree weather. It may even see a blizzard if you've been around last month. So it has to sustain those types of hazards or those types of environments, if you will, as well as the duty cycle. So how often is this thing going to be working? You know, is it 100? Is it 100%? Is it 30%? And those sort of things. You may not know the exact number or percentage of the duty cycle, but you know, in my shift, we have 2 working shifts. So, you know, 5 or 6 to 9 or 6 to 12, whatever that is, you'll know kind of what that duty cycle is that you need for the machine to be running. Now, kind of putting a little bit more spin on stuff is a vertical form, fill, and seal machine. And you guys may, gals too, you guys may have these applications out in your plant. But for this style here, you see that there are 2 pulleys on side to side with a belt that's going to be connected. So to size up that servo motor, you would have to get a few dimensions here. You've got your pulley at the top, the pulley at the bottom. You have the diameters, you have the thicknesses of those of the material as well, of the pulley. Don't forget the material, because aluminum is different and it affects it from steel. The belt, you know, there's the belt size and weight and length and so forth. We can put all that and start doing some good sizing from it. And again, if you have software that's already doing this, you can generally get how much current or torque is needed for the particular axis. Move on to the very right-hand side there, you see that's the back of the machine, and that's actually doing the top sealing of this bagger here. So that one has some sort of an open and close valve that's going to be going back and forth as well. Your true typical vertical form, fill, and seal machine. So it's bagging anything from small, say peanuts, to, you know, dog food, cat food, that sort of thing. Let's not forget, on the same vertical form, fill, and seal machine, that a servo is doing what's called a pull or a film pull, where it's feeding in the film. There's some tension that's going on up top, but you want to maintain that. And so right here you have the 2 pulleys. There's a ratio between these 2 here that it's actually pulling. And so we want to be able to size that appropriately. You don't want to go too big, but then again, you want to make sure that it has enough torque to maintain for the speed. Let's get really big. Let's do some large presses. So on the left-hand side, you notice that there's a rotary of some sort. So there's some sort of a rotary application or rotary motor that might be useful in that sense there to rivet or to drill some holes, as well as the indexer that goes in and out. So that could possibly be a servo motor application as well. Just things to think about as you're going through the plant and wondering. And let's not forget the really good ones, the hand sketches, right? Like, who doesn't love hand sketches? I do. I hand sketch all the time. I do, you know, just have to draw, just have to doodle or do something. But something like this, you know, you've got some concepts you're thinking about. How can I make my machine better? How can I make it faster, work, and so forth? So it's always good to be able to go through these types of sketches. You may say, well, I've got, you know, my payload is going to be up here. I do have the 2 drum rollers that are bound over here. We could maybe add a little idler roller at the bottom. And then there's some sort of palletizing machine that's going to be on the left-hand side. You know, who knows? But that's what R&D is. So we can go from there and at least take some specs to know what we want to do to size it. All right, as promised, it's Michael's turn now. So we're going to talk about some gearbox selection and some important tips.
Excellent drawing as always, Sixto. It's always a good idea to make a hand sketch, especially when you're trying to understand the key concepts. Mm-hmm. And speaking of key concepts, let's talk about gearboxes for just a second. So why do we need a gearbox? Why is a gearbox necessary? Well, there's 3 things that typically are accomplished by using a gearbox. 1, you're going to reduce the overall output speed. 2, you're going to increase the overall output torque. And 3, odds are you're going to decrease the motor size. All of these are very good things for the right application. Now, Sixto gave you a shameless marketing plug. I've got to do the same thing here for just a minute. Yaskawa has gear motors that are assembled at the factory at our facilities in Ohio. We have very common ratios that are available and can build these to your spec as necessary. So depending on what servo motor you're needing, what gearbox ratio you need, we can usually put it together for you. So again, utilize that feature for us. We can definitely help you save some time and money. It also is worth mentioning that when a gearbox and motor are assembled by our team, they're covered by our warranty as well. Now, before I move on, I also want to tell you that not every servo application needs a gearbox. It is very possible to direct drive a motor directly to a load. Take, for example, the horizontal ball screw application that we looked at first. It's very common to direct drive a servo motor to a ball screw in that example, because again, you actually have some speed reduction that's occurring with the ball screw itself. So again, not every application is going to use a gearbox. But if you find yourself sizing an application and the motor sizes are just getting gigantic, or the motor speed is just way down in the dirt real slow, that may be a really good opportunity for you to use a gearbox to help you out. Okay, another thing that's really great about using a gearbox is the fact that it reduces reflective inertia of the load to the motor by a factor of the square of the ratio. So if you're using a 10-to-1 gearbox, guess what? That's a 100 that's a 100% reduction in that reflective inertia. So it's going to help out a whole lot if that's a problem for you too when you're sizing. Now, I'm going to tell you a rule of thumb as well. As a sales engineer who's been doing this a long time, it's always best to try to start with a 10-to-1 ratio for your gearbox if you're going to have to use one. And here's why. As most of you are already aware, gearboxes are set up in multiple stages. You have single stage, 2-stage, 3-stage gearbox, etc. 10-to-1 is the highest ratio you can get in a single stage gearbox for most manufacturers. So if you're going to have to use a gearbox anyway, if you use one like this, it's going to give you the most bang for the buck and give you the most value. So use that 10-to-1. It'll also help you reduce your motor size, and odds are you'll be able to balance that motor size and that cost of the gearbox really nicely with a 10-to-1 reduction. So again, shoot for a 10-to-1 reduction. If you can't get it done there, look at what you can do to change that. Maybe you need to go to a higher ratio. Maybe you need to go with a bigger motor, etc. So now, Sixto, tell us a little more about where we can find more information on Yaskawa Motion.
I'm so glad you asked, Michael. So again, in the chat window at the very top, we have put in these specific links because I know you're not going to remember what CQP8, whatever. So if you want to click on those YouTube links, we have a lot of videos, like a ton of videos that we go through on sizing basics. We do basic concepts as well. I'm going to take it from the ground all the way up, way more than what this surface level webinar is going to be on sizing. But let's not forget, we also have the sizing software. So this sizing software is, I'm just going to say, it's really good. It's really good. So you can put in quite a few different mechanisms in there and get some really good results. And well, actually, probably we're going to do that here in a little bit, but the sizing software is one that you should be able to download and be able to just feel free to play around in there. Size up hypothetical applications and so forth as to what you need. And who do you call for help? Ooh, that's a good one. So your first line of defense should be Innovative IDM, for they are the distributor for Yaskawa as well as an integrator as well. They're a great channel partner for us. We work hand in hand on many different applications. And if ever you need to speak with one of us, Michael or myself, the Yaskawa Motion Division would be another source to be able to reference as well. Now, as promised, we got a little bit of time, so let's go through a live demonstration. And I think we just picked this one out of a hat, okay? But let's say that you have a 3D printer application that you want to size. For instance, maybe a Creality Ender 3D. You're like, about this thing using steppers. What would it take to use some servo motors? That would be cool. So this is just a hypothetical, but no, I shouldn't say it's hypothetical. We've done a couple of these, so we want to look and see a payload of that x-axis at the very bottom there. Maybe it's going to handle 30 pounds. Could be more. We can adjust the sizing software or the file as we need. The orientation in this case is going to be a horizontal. The speed, the specs for this particular 3D printer is about 60 millimeters per second. And the distance, 200 millimeters, give or take. We may go a little bit shy of that. It's going to be an inside, on a desktop somewhere. or I'm sorry, a desk somewhere kind of sitting indoors. Duty cycles, hey, you want this thing to run 100% or 85%, that's okay. And then the material. So we got to know what we're moving, the payload and so forth, or not the payload. We got to know what the ball screw is. And in this case, we're going to just say that the outer diameter of that ball screw is about 12 millimeters, almost half an inch. The material is going to be steel, and the length of it is a full 200 millimeters because that's the distance that we're going. So if everything works well, we should be able to get out of here, and we'll start going through the actual sizing software. So I'm going to get out of the camera for just a second, probably even stop the camera, and just start to go through the sizing software. All right, let's see. Pepper, this should work. All right. So again, the sizing software is free for download. And what you find at the very beginning is just putting in some credential items. Maybe you have some information that you want to send, or put in your name, company name, email address. And then there's some application notes. You may want to type in, this is a 3D printer prelim. All right. Be sure and save, because you always want to do your saving of the file so you can back up your stuff. But in this case, I'm going to continue on. So we mentioned earlier that there are different mechanisms for various applications. So just to kind of go through these, we've got a ball screw, we have a belt system, there is a chain and sprocket, the rack and pinion that we had shown earlier, a roll feeder. These are also typical in a lot of different applications. We have a linear motor that we can put in as well. If we want to go kind of basic and just do some rotary tables or rotary applications. And there's even a cool one here for a crank application, whereby you can size up a crank mechanism. In this case, we're going to stick with the ball screw. It may be a general one, but it's pretty simple. Load mass, so right here is we put in what that load mass is going to be, and I think we decided on 30 pounds. Maybe the part is no more than 20 pounds, and maybe the plate there is another 5 or 10, so we'll just say 30. There's no external force, but we're just going to touch on the main ones that you want to enter into the sizing software here. So the coefficient of friction, the materials, we'll do a mechanism, the ball bearings in there, so we'll just keep that coefficient of friction low and say accept. Now, this is not vertical, so we're going to keep this inclination at 0. That's a horizontal. This lead, so we want to know how many units are we going to move of travel in one revolution of that ball screw. So let's keep it at in inches. We can change the inches here. So we'll say 1/4 of an inch. One rev of that ball screw is going to be 1/4 of an inch. And now we actually have to find the inertia of what we're rotating, as Michael had mentioned in his slide there. You can change this name here to a ball screw if you wanted to, or whatever name you want to give it. These units can change as well, but we'll keep it in millimeters for now. And let's just say the height of this is 180 millimeters. You could put 200 as well. We'll just put 200 for the entire length of that ball screw. The outer diameter we mentioned was 12 millimeters, but we'll just say 12 millimeters there. And then the material. So we have quite a different material selections here. We want to pick the stainless steel and keep that. And that gives us inertia of the ball screw. And we'll say accept. Now, at this point, your mechanism is pretty much done as far as what you enter into the sizing software. We want to leave the gear ratio at 1:1 just for now to see how big of a motor do we even need to run this thing just by itself. Let's move on to the profile editor. This is cool. So the drop down here, if you just select a trapezoid, it'll give you a third motion profile. We can change these user units to millimeters per second. We did say that I believe that Creality Ender was at 60 millimeters a second, but we want to go the total distance. So 180, let's do 200 millimeters. And in the acceleration time, we want to get that up in the half-second range. You want to get the speed pretty quick. So you can see that the motion profile is starting to build upon itself here. You can take a look at different options or deselect some of these options. So the position, if you don't really care about the position just yet, you can look at your velocity that's going on here. You can look at the motor speed to actually know if your motor is going at the speed that you you believe it should be. Let's bring back motor position there. And then it's always important to do a return move. In this case, we'll just keep it at 1 second. And then the return move is just negative of everything that we've done there. That real quick. In crunch time here, 200. There we go. So again, I'm just copying these same numbers in here. All right, so let's say that's a return move, and the dwell, we'll just leave it 1 second. So now we want to look at what are our motor results. Now, it does give you a bunch of information here. We're just going to uncheck all this stuff here and just look at the Sigma 7. So Yaskawa's Sigma 7 series is the latest and greatest. And we want to uncheck this torque factor of safety because we want to look at what amount of torque do we really need to move this motor. And we can display what the required values are for the application. So the required is right here. What the motor has is here. But then let's also do the factor of safety. I like color. And usually green for everything is good. So if we look at, let's just say this 7J 200 watt motor, we can see that there is enough factor of safety for the required rated torque, the peak torque, the same thing for the required rated speed and the peak speed. But the thing that we want to pay attention to is this inertia ratio. So this is a pretty low one here, very, very low, which means that the motor has more inertia than the load, which is fine. We can still work with that. And then in the speed torque curve, we give the ability to look at what's in the continuous region and what's in the peak region. This is a good one to just verify that you're not outperforming the motor by any means. The last tab is this regeneration tab. Now this will give you if there's any sort of regen that's needed. And typically on horizontal applications, you don't get that. The equations would be here in this tab as well so that we can verify that sort of thing. Once you save your application, you then can get what's called a PDF report. It'll give you a little report that spits out how all your application is running. You can kind of give this to either your customer, OEM, different specs and so forth as to what the sizing file will entail and how it moves, as well as the rated data of the motor and the application. So with that, I think I'll pass it back to you, Pepper. I think we're hitting the 30-minute mark or 35-minute mark. I wanted to leave some time for some Q&A, if that's okay.
Yes, sir.
All right.
I had a couple of questions that came in on a direct message. One of them was they want to know about the Sigma sizing software. Is that free that you were just using or what?
Yes, the Sigma Select sizing software is free for download for anyone. I believe it runs on Windows 7, Windows 10, and anybody can download it. My 8-year-old son can download it as well.
Great. Anybody else has any questions, go ahead and type them in at this time. I had one more for you, Michael and Sixto. Says, I have a rotary table with 5 stations. Good for servo, yes or no?
Yeah, that's an excellent application for a servo. As you could see earlier, that's one of our templates we already have pre-built in our sizing software. So that's very helpful as far as that goes. The nice thing too about using a servo for a rotary table is that we can handle the inertia of turning back and forth, or we can go all in one direction depending on what the needs are. So yeah, that is a very good application for a servo motor. Thank you for asking.
Great. So if we went to the beginning of this, somebody came in and asked about a valve actuator. I believe it was Weston that asked about it. Is that a great application as well?
Yeah, that's actually very similar to a rotary table when you think about the mechanics of it. You're still turning one way or the other, and let's say even if that valve has a little bit of an offset for where that main mass is, we can account for that as well. Depending on the industry too, we have folks that can help you provide ruggedized versions as well for our products. So yeah, those are all things that are well within our wheelhouse. Down here in Texas, I feel like we have a lot of valve actuation questions, and the unique thing that servos provide to that is we can really size those servos in really well for valves to where you are maximizing the use of that torque when you first need it to open that valve, and then reduce it down real low once the valve is already moving. So there's a lot of Servo can offer in an application like that.
David had asked about a palletizer. Can you comment on that?
Yeah, so palletizers are one that could be, you know, in a gantry style, let's say a T-bot style, where you really only have an X direction and a Z direction, where you're going down to pick up a bag or some sort of product and move it over to the left or the right side or wherever it's going to be to drop it off. In most applications, you don't need a full six degree of freedom robot. You could do the same sort of thing with some sort of end effector and a T-bot style gantry, where you would have a ball screw that's going back and forth, or rack and pinion going back and forth for the X, and then going in the down direction would be maybe a ball screw as well on both sides. But in any case, we have templates that can work with palletizers where we can we can go in and size those types. So there's an excellent application for a servo motor.
Well, hey, we're at the 39-minute mark. How about that? Appreciate everybody coming. This webinar is also available on demand. Everybody who's on this is in the room today. I'll send you an email where you can access the video on demand and share it with any of your coworkers or teammates that might want to catch this, when they have the time to look at it on their own time. And so, Michael and Sixto, thank you so much for your time today. We appreciate it. And we will close off the webinar now.
Good. Thank you, Pepper.
Thank you,
everybody.
Appreciate you joining in.